You know, in the big push for clean, renewable energy, we're always on the lookout for the next game changer. We've got our trusty silicon solar panels for sure, but the hunt is always on for something better, something cheaper and way more efficient. And that's where this really fascinating new material comes into the picture.
I mean, really think about it. What if we could make solar cells that soak up more sunlight, cost way less to produce, and could be integrated into almost any surface you can imagine? That's the huge question that's fueling one of the most exciting fields in science right now.
So here's what we're going to cover. First, we'll get into what this new material actually is and, how it works its magic. Then we'll look at its incredible promise versus its one massive problem. After that, we'll see how scientists are racing to fix it, and finally, peek into the future to see what this could all mean for solar energy.
All right, so what exactly is this stuff that has the entire scientific community buzzing? Well, the word perovskite isn't one specific thing, like gold or iron. Instead, it refers to a special kind of crystal structure. Think of it like a specific recipe or blueprint for arranging atoms. It has this ABX3 formula, but you can swap different elements in and out. And it's this unique, super flexible structure that gives these materials their amazing properties.
And yeah, these materials have some serious superpowers. They are absolutely fantastic at absorbing sunlight and are incredibly good at turning that light into electricity. But here's the real kicker. They're great at moving those electrical charges where they need to go. Both the positive and negative charges can zip across long distances inside the material, and that is a key ingredient for a crazy efficient solar cell.
And the wildest part? This has all happened blindingly fast. The very first time it was used in a solar cell was only back in 2009. Just 3 years later, in 2012, a huge breakthrough with solid-state designs kicked off a research explosion. So in a little over a decade, these perovskite solar cells, or PSCs, have gone from a lab curiosity to a technology that is giving traditional silicon a serious run for its money.
Okay, so how do these cells actually take a particle of light, a photon, and turn it into electricity you can actually use? Let's break it down.
It all boils down to 4 key steps. First, that perovskite layer just soaks up sunlight. This energy knocks an electron loose, creating what's called an electron hole pair. Just think of the hole as the empty spot the electron left behind. Now, the whole goal is to pull them apart before they snap back together. The electron gets whisked away to one layer, and the hole goes to another. Once they're separated and collected, that flow of charges, well, that's electricity. Let's look a little closer at that separation process. So light hits the perovskite and boom, an electron is set free. It's immediately funneled onto a one-way electron superhighway. At the exact same time, the hole it left behind gets sent down its own dedicated hole superhighway. It's this incredibly fast, efficient sorting of traffic that is the real magic behind how this all works.
Now, to make this happen, researchers generally use 2 main designs. The one up top, the mesoscopic structure, is kind of like a microscopic sponge. It uses a porous framework to create a massive surface area for soaking up light. The one below it is the planar structure, which is more like a simple, flat-layered sandwich. Both of them work great, but that simpler planar design is what really opens the door for making these things flexible and super easy to manufacture.
So, we've got this incredible material that works like a charm. But you knew there was going to be a but, right? With any new tech, there's always a catch. And for perovskites, it's a really big one.
But first, let's just talk about that promise. Perovskite solar cells have hit a verified power conversion efficiency of 25.2%. Now, to put that into perspective, that's already competitive with many of the silicon panels you can buy today. And it's getting better all the time. For a technology this young, that number is just, wow. It's truly remarkable.
And then there's the problem. This quote right here really says it all. For all their amazing efficiency, these cells have an Achilles heel. They just don't last very long when you put them out in the real world.
So this is the core trade-off right here. On one hand, you have absolutely record-breaking efficiency and the potential for cheap, easy manufacturing. But on the other hand, you have a material that falls apart when it gets wet, gets hit by the sun's UV rays, or just gets too hot. You know, all the things a solar panel has to deal with every single day.
Let's meet the main culprit, shall we? Moisture is public enemy number 1. It literally causes a chemical reaction that ruins the perovskite. Then you've got UV light, which can damage one of those key transport layers we talked about. And finally, high temperatures. We're talking as low as 85 degrees Celsius or 185 Fahrenheit can cause the perovskite crystal to just decompose. Not great.
So this is the great puzzle for perovskite researchers.
The potential is absolutely massive, but only if they can crack the code on durability. And believe me, the race is on to do exactly that.
All right, let's take that first problem. How in the world do you stop moisture from wrecking the most important layer of your device?
Well, scientists are coming up with some really clever defenses. One idea is to slip in an ultra-thin invisible raincoat, a tiny protective layer of something like aluminum oxide that just blocks water. Another cool trick is to use electrodes made of carbon, which naturally hates water. It's hydrophobic, so it actively pushes moisture away, protecting all the sensitive stuff inside.
And they've got strategies for the other bad guys too. To fight UV damage, they're often just swapping out the weaker material for tougher alternatives that can handle the radiation. And to beat the heat, they're experimenting with reinforcing the whole structure with incredible nanomaterials like carbon nanotubes and graphene, which makes the entire cell way more resistant to high temperatures.
So with all this incredible progress being made, what does the future actually hold? Where is all of this research headed next? One of the most exciting new directions is actually making things simpler. Get this, some researchers have figured out how to build cells that don't even need that separate hole transport layer. In these new designs, the perovskite material itself does double duty. It absorbs the light and transports the holes. This makes the cell simpler, cheaper, and it turns out even more stable. So the to-do list for researchers is pretty clear. They're fine-tuning the perovskite recipe to make it even better at absorbing light. They're inventing brand new materials for the transport layers that are both super stable and cheap to make. And, this is the big one, there's a huge effort to find a way to replace the lead in the formula with something less toxic and much safer for the environment.
And that all leads us to the final billion-dollar question. The promise of perovskite solar cells is just undeniable. A future of cheap, incredibly efficient, and versatile solar power. The only thing standing in the way is durability. So the great challenge and the great opportunity is whether science can finally solve this stability puzzle and unlock that future for all of us.